Welcome back. In this video, we're going to start talking about 4.1, which is all about an algorithm called the closed interval method. It's a three-step algorithm that I'll explain, but it has a very specific goal, and that very specific goal is to find the maximum and minimum value of a function on a closed interval. And remember, this word value means output. So remember, what's a closed interval? This is all the inputs between A and B, and the fact that it's closed means that I include A and include B. So really the goal here is to say, if I put in every input starting at A and ending at B into F, what's the biggest number I would get out, and what's the smallest number I would get out? Now, you'll recall from the last video that we talked about these things that we called a local max and a local min. And for the most part, our biggest value and our smallest value are going to happen at a local max and a local min. But if I want to distinguish between the term local max and local min and the thing I'm finding in the closed interval method, I'm going to either use the word absolute or global. I'll also call this the absolute max or the global max. Okay, and I will call this the absolute min or the global min. Okay. I won't always do that, but if I want to be super clear whether I'm talking about a local max or one of these kinds of maxes, I will do that. Just for emphasis, to show you what this would look like in a graph, I might have this point. This point is a local max, but it's not the max of the function, because this max over here, it's bigger. So that's the distinction I'm trying to make when I talk about local maxes and global maxes and all of these things. So, as I said, this is a three-step process. And once we've talked about the process, I'll explain why it works. So the first thing you have to do is find all the critical numbers of f of x. But note this thing, I'm only going to find the critical numbers of f of x that are actually in my interval. And I'm going to go ahead and write those down. I'll just give them made-up names, C1, C2, up to CK, whatever they happen to be. The next thing I have to do is decide, okay, these are the inputs, which of the outputs is the biggest? But I also have to, and I'll show you some graphs in a minute, I also have to check the endpoints. So I'm going to check f of A, f of C1, f of C2, f of CK, and f of B. So, in practice, usually there's going to be one critical number or two critical numbers. And so when you do that, you'll go ahead and you'll find the value of the function at the two endpoints, A and B, as well as the critical numbers that are in between. I'm going to note these things go into the function, not the derivative. Now, last step is actually pretty easy. The last step is, well, these things are all values of the function. The max value and the min value are already in this list. So the max value is the biggest of these numbers, and the min value is the smallest of these numbers. So to help clarify this, I'm going to do a bunch of examples. So here's our function. We've got the function x squared minus x cubed, and the interval 0 to 1. So reminder, what is it we're asking? We're asking, of all the inputs that you could plug into this function between 0 and 1, what's the largest value you could get out, and what's the smallest value that you could get out? So we have our process here to do this. The first thing we're supposed to do is find all of the critical numbers of the function that live in this interval. So this is step 1. So our derivative is 2x minus 3x squared. Can factor a 2x out of that. And so that will give us that x equals 0 is a critical number. And this term here will give us that x equals 2/3 is a critical number. So this is our list of critical numbers. So that's step 1. Find all the critical numbers, and note these two are in the interval. For step 2, I meant to find f of the left endpoint, f of each critical number, but notice I'm already finding f of 0, and so what that really means is if one of your critical numbers actually is one of the endpoints, you can basically ignore it. You're going to check it anyway. In other words, if you like, you can put these sort of open braces here that say, all I really need is all the critical numbers that are in the open interval a to b. It doesn't matter a lot, but it'll save you maybe a tiny smidge of time. So, I will find the value of f at the left and right endpoint, and then the value of f at this critical number in the middle. Now, f of 0, it's 0, and f of 1 is also 0. Remember that in this step 2, where I'm evaluating the function at the endpoints and all the critical numbers, I am always plugging these things into the function, not the derivative. So namely, I am plugging 0 and 1 and 2/3 in here. When I go to find f of 2/3, it's going to be 4/9 minus 8/27. 4/9 is in fact 12/27. So this will be 12 minus 8/27. And so, in fact, this will be 4/27. And then step 3 says, hey, look at all the numbers we just computed. So, namely, the values, this value, and this value. That's what step 3 says to do. From among those, I get to pull out the max value and the min value. So the max value, that's going to be this 4/27, because 4/27 is bigger than 0. And then the min value here is just 0. Now, please note, when you're asked a question about finding the max and min value of a function, this word value tells you that the question is looking for the output, not the input. So in this case, I didn't give 2/3 as the answer, I gave 4/27. And I didn't give 0 or 1 as the answer. Well, I did give 0 as the answer, but I gave that 0 as the answer, not one of those two inputs. If you want to, just to make your answer more complete, you can add something like at x equals 2/3 or at x equals 0 or 1 to tell you what inputs those outputs are occurring at. That's fine. It is not necessary, but you can do it if it will make you feel better. Just make sure you're giving the outputs when the question asks you for the min and max value. Now, I promised I would explain everything that just happened in a graph. So here's a graph of the function f of x equals x squared minus x cubed. The way the closed interval 0, 1 enters this is that I only care about the portion of the graph between x equals 0 and x equals 1. So I have drawn in as dashed lines, blue on the left, green on the right, x equals 0 and x equals 1. And so because this question talked about the interval 0, 1, for the purposes of this question, I'm treating the part of the graph to the left of the blue dashed line and the part of the graph to the right of the green dashed line as though they do not exist. And then, within the confines of just that part of the graph, I'm asking, hey, what's the highest output I get? If you look closely at the graph, you can probably see where that is. Namely, it is up here on the graph where I have circled. Now, from the work that we did, we know that that point must have x-coordinate 2/3, and that the value there must be 4/27. If you're not sure if you quite believe that, you can go ahead and check for yourself that 4/27 is very close to 0.15, which is very close to where the y-coordinate of our point here seems to be. The 2/3 is also believable. Additionally, as we saw in our calculation, the minimum value on this interval is 0, and that minimum value happens at both the left endpoint and the right endpoint. That is, at x equals 0 and x equals 1. When we did the question, we saw that there were two critical numbers, both of which you should again be able to see in the graph. One of them is here at x equals 0, the other is here at x equals 2/3. These are the spots, again, where there's a flat tangent line. These are the spots where the shape is one of those I showed you at the beginning of this chapter. Namely, where the shape is one of these. So if you wanted to describe it, at x equals 0, there's a local min, and at x equals 2/3, there's a local max. The last thing I want to emphasize from this graph is how important the closed interval 0, 1 was. You'll note 0 is not the smallest value this function takes. If I look over here, the function definitely takes negative values. Likewise, 4/27 is not the largest value this function takes. If I look over here on the left, the function definitely takes values larger than that. This interval from 0 to 1 is serving as a constraint. It's telling us what part of the graph we're allowed to look at. And both of these points I have circled now live outside that constraint. So it's important to remember just what this closed interval is doing in these kinds of questions. Not too dissimilar to the example we just did. We've got a function here, and we want to know where its max and min values are on, and now the interval is 0 to 3. So first, we go ahead and find the critical numbers. Namely, in this case, my only critical number is x equals 2, and I make sure I check that x equals 2 is in the interval, and it is. And now I go ahead and evaluate the function at the two endpoints, and the critical number in the middle. F of 0 in this case is 3, f of 2 is -1, and f of 3 is 0. Now, in part 3, I look at just the outputs from the previous step, 3, -1, and 0. And I go ahead and pick out the biggest and the smallest. So the max value here is 3, and the min value here is -1. Here's another example. Let's take f of x is x to the 4th minus 4x squared plus 3. And let's take the interval -3 to 1. And let's find the max and min values as we've been doing. So, first step, we're going to find the critical numbers. So to do that, we have to find the derivative. And we have to solve to find when that's 0. And I can factor a 4x out of there. And so this is going to give me that either x is 0 or x is plus or minus the square root of 2. Here it is important to notice that in our description of the algorithm we're following, we're supposed to only find the critical numbers in the interval. And so an easy mistake to make, especially in a situation like this, is to not notice this point actually not in the interval. So we have to throw that point out. And we have to do that before we proceed on to the next step. In the next step, we're going to evaluate the function at the two endpoints, as well as the two critical points we found that were actually in the interval. Again, the -3 comes from there, the 1 comes from there, that's this point and this point. And at this point I can explain, I always write this in order, starting at the left endpoint, and then increasing until I get to the right endpoint. Now you don't have to do this, But the reason why I do is that then if I end up writing down something that's bigger than the right endpoint or smaller than the left endpoint, that is, if I end up writing down something that's not in the interval, it gives me an extra chance to catch that I've done that. Okay, so filling in our values of the function at these points, we find that f of minus 3 is 48, f of minus root 2 is minus 1, f of 0 is 3, and f of 1 is 0. And now we're ready to wrap up this example, so we just have to look at each of these and identify the biggest and the smallest. So the max value we find is 48, and the min value we find is minus 1. Now, again, I'll remind you, we're giving the outputs, not the inputs, but if you want, you can write here at x equals minus 3, at x equals minus root 2, if you want to keep track of that information. Alright, that's all for this video. In the next video, I'm going to do more examples of this where we pull in some of our derivative rules. That is, where we use the product rule, or the quotient rule, or various things of that sort, throw in some e to the x's, some logs, and go through the same procedure. But probably a good idea to pause at this point, do the first chunk of the homework, and then once you're confident with that, then come back and pick up the videos. But that's all for now. I'll see you next time.